Thanks for having me here today. I'm going to talk to you about some recent research that we did at Google. This paper is going to be published at the AAA conference in February. And it's called Learning to Attack, and where we learn to generate adversarial examples. So I'll start with an overview of the field of adversarial examples. This research really started in 2014, 2013-2014 with this paper that showed that it was possible to generate these examples that looked like one thing that would, convince a classifier that it was something completely different. In this case, we have a panda image on the left, and then we do make a small change to it, and then the network is convinced that it's a given, a type of monkey, very confidently. So here's a working definition of adversarial examples. Adversarial examples are modified versions of valid inputs that cause a classification system, or a system in general, to change from correctly handling that input to incorrectly handling the modified input as judged by a human observer. And so that as judged by a human observer part is really important. So to look at that in more detail, so we start with some valid input, picture of a panda. It's correctly classified by the system. And then we make some change, generate some change to that input, this modification or perturbation. And we add it to the original image to give us the modified input. And now the system gives us incorrect behavior, calling it a given. None of us would think that that's a given. So this is different from things like fooling examples, where you just take some random geometric pattern and see what the classifier tells you. And maybe you constructed that pattern in a particular way, but nobody would look at that and think that that's anything other than a geometric pattern, which is not something that the classifier was trained to deal with, or random inputs themselves. Just because of the nature of how these classifying networks work, the network is going to tell you some output. It will give you an output for any input that you give it. So these are, in some sense, very much less interesting than adversarial examples. A third example of this is what is called open world inputs, where you give it an image. It's a real image. This is a bunch of rocks, but the network wasn't trained to classify rocks, and so it's like, oh, well, maybe that's a baseball. So we're going to talk about adversarial examples rather than these other three types of things. So how can we make these things? The original idea is just to do optimization on the input. So specifically, we're going to compute the gradient of some desired output with respect to the input, and adjust the input according to that gradient, and then check to see if that the new image that adjustment gives us causes the network to give the desired output. So this is a really powerful idea, but it's actually extremely slow because you're running an optimizer on every input that you want to change. And furthermore, if you want to correctly constrain the modified input to be like an image, you have to work with really slow optimizers to specify those constraints. So this was the original work showed that it was possible, but it was too slow to really be a practical attack. So then the next step here was to let's assume that these models that we're training are mostly linear, and maybe we can just take a single step in a particular gradient direction, and that will be something that causes the classifier to fail. And that's the core idea of what's known as the fast gradient sign method, which I'll explain in a little bit of detail here. So the idea is that we want to maximize the loss that the classifier has on a particular adversarial example. That adversarial example is x with the tilde on top of it here, and j is the loss function. And so that loss is going to be approximately the loss on the original input plus the gradient of the loss with respect to the original input times the change. And so, like, what does that mean? And so additionally, we need to constrain the example to be close to the original example. Otherwise, like, maybe you changed it to misclassify, but it doesn't look like the original image at all. So we can write that down in closed form and this simple epsilon times assign function is sufficient to give us both the max norm constraint and this linearity assumption. And so now we can just take, we have a closed form formula that lets us go from a correctly classified original input to a modified adversarial input. So this is really fast. It only requires a single forward pass and backward pass through your target network. And it's quite effective on undefended models. I think that probably Alex talked about this some this morning. So it can achieve, some of the models that haven't been defended against fast gradient sign will be wrong maybe as much as 90% of the time when you run FGS on them. So we can actually easily extend this to either targeted attacks or iterative attack. So a targeted attack is just saying that we want the adversarial example to be classified as a particular target class. So instead of taking a panda and just running fast gradient sign on it and getting given, we might say that we want that panda to look like, to be classified as a cat or something. And so that's a harder attack. Iterative attacks, you can take either of these variants of FGS and just take smaller steps and do multiple such steps. So like maybe do 5 steps with a smaller step size. And so iterative attacks in particular are much more powerful than fast gradient sign because they can really hone in on the correct perturbation to change the classification. But they're still much faster than doing an optimization-based attack. So optimization-based attacks still are much more powerful than even the iterated fast gradient sign attacks. So how can we make these faster? Well, mostly they're slow because of this constraint satisfaction problem that I mentioned, where like it has to be a valid image, and you can't give pixels that are like outside of the correct range or whatever. So if we can do that as a soft constraint satisfaction, then we can have full-powered optimization attacks that will give us much smaller perturbations and can actually like defeat really any network. And so the core idea is a little bit of math. Is that instead of working on the input itself, on the input itself, we'll just do a change of variables here, and we'll use this tanh function to make certain that the output of the optimization process is still in the correct range between, in this case, -1 and 1, and then you can scale it to be whatever range you care about. So very simple observation, but it lets us suddenly do fast optimization-based attacks, relatively fast optimization-based attacks that at the time of this research were successful 100% of the time and had much smaller perturbations than anything that anybody had seen before. Okay, so that brings us, that overview and review brings us to the Adversarial Transformation Network, this research that we did. So the core idea here is that instead of doing one of these mechanical approaches like fast gradient sign or running an optimizer, maybe we can just learn to train, we can just train a network to learn to generate adversarial examples against some target classifier or some target network that we care about for any input. The math for this is actually fairly straightforward, even if it doesn't look it. This G function is going to be the adversarial transformation network that we are going to train. And there's going to be 2 components of the loss. The first is this input space loss. So that means like we want to make certain that the adversarial example that we produce is close to the original example, just like in fast gradient sine. And then this f function is just the target network, whatever classifier or that we are wanting to attack. And the second component of the loss is this output space loss. So basically, we're going to have an additional loss term that's based on the output of the target network on our modified adversarial examples that we generate. So there are two variants of adversarial transformation networks. The first we can call perturbation ATNs, and they just learn to generate a perturbation of the input that will cause it to be misclassified. The second are adversarial autoencoding ATNs, and they actually have to learn to generate the entire image, just like training a normal autoencoder, except that the output is going to be adversarial against some target network. So PATNs, perturbation ATNs, produce adversarial examples that are very faithful to the original image because most of the pixels are unchanged. For instance, you look at this picture of a dog, and you can see that it's like a pretty high resolution photo. I don't know how well you can see, but you can see that the fur is all there, and it's lots of detail in the photo, but there's a little bit of weirdness maybe in the lower left-hand corner. And that's an adversarial example from a PATN that's targeting a specific class, which in this case is soccer ball. So you notice that in the lower left-hand corner, maybe there's like the ghost of kind of a soccer ball shape there. And that's sufficient to convince the network very confidently that that's actually a soccer ball rather than a dog. Similarly here, this is actually even a little bit more subtle. Also in the lower left-hand corner, for the same dog, there's just a little bit of perturbation, a little bit of change to the fur there, and that's all it takes to convince the target network that that's a zebra rather than a dog. By contrast, adversarial autoencoding ATNs produce adversarial examples that are much more diverse and actually more effective against the target network. And they're easier to train and faster to train, it turns out. And also faster to evaluate for a variety of reasons. But they don't maintain quite the same fidelity in the output image, since they have to generate every single pixel of the output image. So here, again, we have an autoencoding ATN that is targeting zebra, and you can still recognize that that's clearly a dog, but something weird is going on with its fur, and the network believes it to be a zebra. Probably my favorite is this one where basically adding orange dots to the face of the dog convinces the network that it's a volcano. And so this kind of brings us to an interesting observation with these. When you do the mechanical fast gradient sine type or even optimization-based attacks, you get some very small perturbation that's much less noticeable than these. But they're completely uninterpretable. They just like people look at them and think that they're noise. So I'll show an example here. This is what a fast gradient sine attack on that same dog image looks like. It's just some noise pattern. So in contrast, though, these these images can actually tell us something about what the networks think are important. It's semantically, right? These orange dots clearly have something to do with like lava, and so we can understand that like the networks we've been training have focused too much on lava things for deciding that a particular image has a volcano in it. And that's a weakness that we can exploit, of course, but it's also, it gives us a clue about how we might fix these things. Okay, so looking at a little bit of numbers. So here we have 3 different autoencoding ATN architectures, and this is a table of the attack success rates and the different 4 different target classes that we looked at. And so they actually all do pretty well, 80 to 90%. This is against the state-of-the-art ImageNet classifier. This is Inception ResNet v2 from about a year ago. And fast gradient sign with like a reasonable value for its parameter epsilon actually was only successful less than half the time. And as I showed it, looks like this. It turns out that all the images we pre-picked to demonstrate with, it wasn't able to fool the classifier. Additionally, like once we've trained an ATN, we only actually have to do a single forward pass through our adversarial transformation network to generate adversarial examples. This is so how long does this actually take? In our fastest network, it's 16 milliseconds per image that we do, and a couple of others that actually have poor performance as well are a little bit slower, but the 55 or 61 milliseconds. In comparison, fast gradient sign on that same target network takes 58 milliseconds. So our best and fastest ATN is like 3 or 4 times faster than fast gradient sign at generating these examples. But of course, I mean, that speed is very dependent upon the size of the network and how efficiently you can evaluate the network that you're training. So how long does it take to actually train these adversarial transformation networks? Again, against the state-of-the-art ImageNet classifier, the Inception ResNet v2, on a single GPU, we were able to train ATNs in about 2 hours. It was actually just in 1/10 of an epoch through ImageNet, we were able to train to this performance that I've been showing you. So they train very fast. And in comparison, ImageNet itself, the Inception ResNet model itself takes about a week to train on many GPUs at the time. So like 2 hours compared to a week, these things are very easy to train, which is actually because there's so much signal in the output layer of the network that you're attacking. The ATNs can learn to generate these images very easily. So changing tack a little bit, attacking is fun and entertaining, but how can we actually defend against adversarial examples? This is a big problem for a lot of different areas. Very obviously, self-driving cars, and even things just on the internet, image classification and the like. We would like to not let people fool our classifiers so easily. There are a variety of ideas here. So we could try to improve the models. We could try to make the models more robust to attacks. We could try detecting attacks, or we could try to make more calibrated predictions about our inputs, so that if we're not confident, we at least know that we're not confident. We could also try to improve the algorithms. Maybe there's a way to make better optimization procedures for robustness, or maybe there are better training procedures. Or maybe we should be trying to improve the data. We could try maybe collecting and labeling larger data sets, or figure out some way to leverage unlabeled data. Or maybe synthetic data sets could help us out. If we had really realistic synthetic data sets, maybe that would help us. Or something else that we haven't thought of yet at all. So I'm going to talk about these two things a little bit. How we might make models that are more robust to attacks, and how we might make better training procedures. So this is another bit of research that we did at Google, deep variational information bottleneck. This is really quite unrelated to adversarial examples. The core idea is that maybe we can do classification from an information theoretic perspective. And so what does that mean in this particular case? If we're given some input distribution, some input set X, and we're going to map it to some hidden, some latent space Z, and then try to classify from Z to our actual target classification labels Y, then we want to maximize the mutual information between z and y, while minimizing the mutual information between x and z. So graphically, this is if we have some encoder function that takes in our input x and outputs this representation z, then we want to make certain that the mutual information that is present, that our encoder maintains between x and z is as small as possible, but that the classifier built on top of that representation z maximizes mutual information between z and y. In other words, like, that's kind of a technical description, but intuitively, all we're saying is that we should try to forget everything irrelevant about the input x when we encode to this new representation z. Everything irrelevant for classifying x as a y, but then remember everything else that is relevant for that classification task in our encoding z. And so if we can figure out a way to make our networks do this, then you might imagine that this would make them more robust to adversarial examples, because they should be ignoring all of this extraneous noise that adversarial examples add that is in fact irrelevant to the classification task. So we looked at this again on ImageNet. So here we have a set of the original inputs from ImageNet's validation set, and in green is the original class ID. And then, so here are some targeted adversaries against that same inception ResNet model. And you notice that, like, there's really no difference between those images and these adversarial examples that I'm showing you here in the original images. If I go back, you really can't see anything changed. And to illustrate that, this black image on the side here is the set of perturbations, which are very small, very hard to notice. And every single one of these images is a successful attack against inception ResNet v2. And in fact, so these adversarial examples were all generated using the full power optimization attack that I described earlier. So that attack is able, against normal networks, is successful 100% of the time. It's a very powerful attack. So if we, instead of using the standard inception ResNet v2 model that we're using there, if we just train a new layer on top of that, that's a variational information bottleneck layer, and then run the exact same attack on it, we get attacks that look like this. And on the right-hand side again is the perturbations. You notice that they're much, much larger. And more importantly, all of these images that have purple boxes over them are failed targeted attacks. This optimization attack that works 100% of the time on every network we've seen before actually fails about 50% of the time against the VIB model. So Alex talked about this in some detail this morning, but I'll give my perspective as well. There's this really great idea of adversarial training that while we're training the model, maybe if we just show adversarial examples to it with the true label that it should have, so that we can train the network to correctly classify these adversarial examples, maybe that will make the networks robust to this stuff. And of course, the adversary needs to be fast for this to be useful. So fast gradient sign was the first time this was actually kind of a thing that could be reasonably explored. And it turns out that this does work. For using adversarial training with fast gradient sign, you can substantially improve the robustness of the target network against fast gradient sign adversarial examples. So here are some numbers from Alice's paper, where without adversarial training, we see that like FGS can successfully attack over 40% of the time, but with adversarial training, with FGS, the attacks are successful less than 10% of the time. But training with fast gradient sign doesn't confer robustness particularly to adversarial examples generated with more powerful attacks. Even the simple iterative attack is unfazed by adversarial training with fast gradient sign. And numerically here we see that without adversarial training, the iterated attack is successful maybe 80 to 90% of the time, and with it, it only drops down about 10%, 10 percentage points, maybe, not even that much. So FGS training didn't really help us out much in defending networks against more powerful attacks. So of course, the next natural thing to do is to try training, do adversarial training with FGS, with iterated attacks. And this is interesting because you can view this as actually a search for a saddle point in the between the strongest adversary and the network. It feels a lot like actually generative adversarial networks in some sense, mathematically. So this rho of theta function is just a function to estimate the strongest adversary for the network. And the L function over here is just a loss function on adversarial networks. And so this table is showing us fast gradient sign adversaries and these iterated adversaries. And without adversarial training, fast gradient sign is a good attack. The iterated attack is a very good attack. It's 10 times more effective. With FGS adversarial training, we get we can get the performance of the network up to 95%. Only 5% effective FGS attack, but it can't handle the iterated attacks at all. But with iterated adversary training, we can get the performance up to about 50% on both of them. So it's a pretty substantial improvement. But it's still not that great. We'd like to have better than 50% chance of getting things right when somebody shows us an adversarial example. So to bring it back to the original topic of learning to attack in adversarial transformation networks, I'm going to speculate a little bit now that maybe we should be training something like a VIB model that I talked about that's more robust to these attacks kind of naturally. With adversarial training using ATNs instead of, or in addition to something like FGS. And because these ATNs train so quickly, you could imagine a procedure that we train a set of ATNs from a given checkpoint of the network that we're training, which again, the network we're training maybe takes a week to train, the ATNs take a couple hours to train. So choose some checkpoint, train a set of ATNs, and then use the output of those ATNs as the adversarial examples that we want to train the network to correctly classify. And we might expect the accuracy of the target network to go up on those examples over time. And so at some point we decide that the network, a particular ATN is no longer valuable, and we replace it with a new one. So then we're done, profit. Maybe this solves our problem. Maybe this will solve adversarial transformation networks. Again, this is speculation. We haven't done this set of experiments yet. If somebody wants to work on this with us, I'd be very interested in talking to you. Yeah, the core thought here is that the reason this might be more effective than fast gradient sign based or these kind of mechanical methods for adversarial training is that these ATNs generate a really surprising amount of diversity in the adversarial examples that they generate compared to them. It doesn't, as I said earlier, it doesn't just look like noise. It looks like all sorts of different things that are sometimes very surprising, and sometimes very kind of semantically revealing that they tell us what the network's doing wrong. Here on the right-hand side, again, this is 4 examples from fast gradient sign, and they all look the same in that they all just have some noise added on top of them. None of them were successful in this case, which is why they're outlined in green rather than red. And on the left, we see a collection of successful examples against the same images using generated by a variety of different ATNs targeting 4 different target classes. And it's a little bit hard to see in these slides, of course, but if you look closely, they differ from each other quite dramatically. So maybe that will help us defend against this pretty massive weakness that we currently have. And that's all I have. Thank you. Any questions?
See, I'm the one that has to beat the questions out of you guys. Any questions? Come on. I guess you're off the hook. All right, well, thank you so much, Ian. Before you leave, we do have a gift for you. We're going to have Chu Chen Yun come up and present you the gift. It's really heavy. I don't know if you've seen everyone else. Oh, you probably saw his. I saw it, and I was thinking, there's no way it's that heavy. And I'm not exaggerating, it is. Some is going to be stuck in everyone's heads tonight. See, I told you.
Thank you.
I just want to pass it around so everyone knows we're not being dramatic. Thank you very much, Ian. Thank you.